Okay, so we are done with the first order systems completely, and now let us move to the second order systems. Second, hold on, guys, hold on. Let's continue. So second order systems. So in the first order systems, you saw that when you have an input to the system, what's that? What's that? Do you have a question? Hello? Can you hear me? Oh, okay. Okay, can you hear me now? Yes? Okay. So in the oh, what happened? Okay. So in the first order system, we saw that when you have input, so you have a gradual movement toward the input, and there is no oscillation here. See what I'm saying? Even when we had the impulses input, so we had this kind of response. There's no oscillation here. Okay? Or for the ramp, we had transient response, but it was a transient, but no oscillation and going like this. Or for the parabolic, we had this. Okay? So the characteristic of the first order systems was transient response, transient response has no oscillation. Okay. But when you increase the order of the system, eventually we're going to see the oscillations. Okay. So what I'm gonna, the big picture of this part is that I'm gonna show you if you have a mass spring, and this is the mass. In the first order system, I eliminated mass M, Kc, and if I say here is Kf of t, this system equals to R, L, and C input voltage plus minus R inductor, this is inductor, and the capacitor, and this is equals to, okay, and this is equal to, so tank of the water in series. H1, H2, R tank 1 resistor, R tank 2 for the valve, CT1, CT2, Q in and Q out. All of these, they are second order system, and they are the same system. They have the same dynamics. So if you want to design a board to control the mass spring and damper, you can calibrate the input voltage. If you go to the vibration lab that we don't have here at SDSU, you can calibrate input voltage with the force and the rest with the mass spring and damper. So I'm going to show the next few classes, I'm going to do extensive analysis on the second order system. Then we're going to move to the higher order systems. Clear, everybody? Yes? Huh? So let me go to the next page. Can I go ahead? Yes or no? Okay. So let me start with the second order system, the first one. The guys that you had the vibration course with me, probably you know this, but I'm going to transfer everything to the frequency domain, not the time domain. So K, C, and this is K, F of t. Of course, this is recording, right? Yeah. So obviously, this is the X direction. So it's gonna move as X, and here's the origin of it. Okay, origin. So if you apply the force, you know that there is a, as we did in the previous case, this is the reaction force of the spring and the reaction force of what? Damper. So applying the Newton's second law, sum of forces in x direction is mx double dot. In the previous case we had no m, but here we have m. So you have mx double dot. So this says that you have the second time derivative. So it says when you go to Laplace transform, you have s squared. Remember the Laplace table that I provided to you? So your system is second order system. Equals to, so here is positive, this side is negative, obviously. So this is negative, minus Fs minus Fc plus external force input to the system in the control systems. I'm talking about. So it is mx double dot, knowing that this is the linear spring is minus kx, as you know, linear damper cx dot plus k f of t, or mx double dot, this is standard, it is cx dot. Yes, yes, exactly. So when I say 10th order system, means you have 10th order derivative. You have this xn. See what I'm saying? So we're gonna go there. We're gonna go there eventually to the fourth order system. We're gonna have example, but I think in the March end like that. Okay. So it's kx gonna be k f of t. So because we are going to the frequency domain, my assumption is that the initial condition for the x is 0 and for the velocity of the mass is 0 for simplicity. So if you apply the Laplace transform, you have this m. Oh, before going to the Laplace transform, let me play with this a little, because those of you that you had no vibration with me, so you have to know about this. Okay, guys, if I divide everything by m here, you're gonna have x double dot plus c over m x dot plus k over m x equals to k f of t. Okay, we know from the pendulum problem, look at here guys, that I taught you. Remember that I taught you this? Yes? Pendulum problem in the first class. What was the name of this? I want that all of you go and find for me from your notes. What was the name of this? Yes. So the coefficient of variable, not the second time derivative, which is 1, is omega n squared. So this is again, for mass spring damper, is omega n squared. So this is x double dot. So natural frequency of the system is K stiffness over M. Okay. Yeah, obviously. Thanks for listening. Okay. So the name of this is 2 zeta omega n. 2 zeta omega n. What is that? So in the vibration of mechanical system ME4, what? Yes. So zeta is C over CC. This is a non-dimensional number. Why non-dimensional? Because damping over damping, because dimension is 1. So the name of this is damping. Why damping? Because C is damping coefficient. Ratio. CC is critical. This C stands for critical. Critical damping coefficient. So I'm going to show how to calculate. Bear with me. But for here, I'm saying that it is 2 root square of Km. Damping ratio. Okay. So let me show you this. So 2 zeta C over 2 Km multiplied by natural frequency K over M. This with this goes to New York. This with this gonna be M. This with this is gonna be C over M. Here we go. You see that? Yes? Yes, exactly. Always. For second order systems. Always. So I am transferring your dynamic of the system from K, M, C to meaningful parameters. One of them is natural frequency of the system. Another is the non-dimensional number, namely damping ratio. So you see in the other side of the equation, K over M is also what here? Natural frequency score. Why I'm doing that? Because I'm going to explain to you now. Can I go to next page? Yes? So because when I'm writing this as x double dot, when I'm going to the MATLAB for coding and simulating, it's going to be very interesting. It's going to be 2 zeta omega, and zeta is like this. Right here, zeta is zeta. It's Greek letters, right? Zeta. 2 zeta omega and x dot plus omega n square x equals to omega n square f of t. So after this, and this is valid, as I'm going to show you guys, and this is valid not only for the massive spring damper, for the RLC circuit, for tank of the water in series, meaning that your RLC circuit has natural frequency to oscillate. Your tank of water has natural frequency to oscillate. Your RLC circuit has damping ratio. The tank of water in series, they have damping ratio. That's why the name of this system is the modeling of physical system. In this course, you learn how to find the similarity analogous between the systems and analyze only with one equation. I don't care that this omega n is K over M, or I don't know here. So I didn't memorize it. I'm just giving as an example. Or L over CR, or natural frequency of the system. I don't know. Just example. RT1, RT2, for example. Okay. 2 CT1, CT2. I don't care about these numbers. I only care about this. See what I'm saying? So I'm generating a universal differential equation expressing any stable second order system in this format. For example, for this system, zeta damping ratio, probably, I don't know, it's gonna be, I don't know, RC over 2L. We're gonna drive together eventually. I don't care about these numbers. I care about this non-dimensional parameter. Why I do care about that? Because based on this differential equation, you have three types of systems after this. For second and higher order systems, when the damping ratio is smaller than 1, we name this technical name. Even in the vibration course, if you come, underdamped systems. Not underdamped massive spring damper, not underdamped RLC circuit, not underdamped robot, not underdamped satellite, underdamped systems. So this is a universal sign for us. If a system has zeta is smaller than 1, is underdamped systems. Means, what does it mean? As it says, damping is not enough, is under our need. So what does it? Yes. So you're gonna have oscillation in the system, in the transient response. Oscillation. As your friend says, it's gonna overshoot. Then we have this. Zeta is 1. We're gonna say critically damped systems. This means you have enough, but oscillation goes away. Oscillation goes away. And response is slower. We're going to derive mathematically. Slower respect to this case. Then zeta is greater than 1. If this is under, it's going to be named overdamped systems. Means you have damping extra. Again, oscillation goes away and is much slower response. So this is universal definitions for second and higher order system that they are stable. When I'm saying stable, means that based on the Rolls stability criteria that I'm going to teach you. But for now, when I say the system is stable, meaning that the first condition, all the signs exist and they are positives in the left hand side. All the signs exist and all the coefficient exist and is positive. On the other hand, if I say this, as I taught you, this is not stable because we are lacking x dot. What was this? Remember, I taught you in the first class. Pendulum. It was marginally stable. See what I'm saying? Yes? Yes. Because the poles of the system, remember, you had poles on the imaginary axis. And I'm going to explain this to you one by one. Okay? Real, imaginary. See? And there's no steady state error because it's oscillating forever. That's right. So, having that, now let's go back. Can I go to the next page? We're going to examine one by one of these for different input to the systems, mathematically and in Simulink and MATLAB. So, can I go ahead? Okay. So, having that, now we have x double dot plus 2 zeta omega n x dot plus omega n square x equals to omega n square f of t. So if I apply the Laplace transform by knowing that the initial conditions here is 0, right? So Laplace of the x double dot, based on whatever I taught you, is s squared x of s, and the rest is 0 because the initial condition is 0, plus 2 zeta omega n s, the first time derivative, x of s. Every time derivative give you this. Remember, I taught you. Go to the tables of the Laplace. Omega n squared x of s, omega n squared f of s. So on the other hand, x of s, if you factor out, gonna be s squared plus 2 zeta omega n s plus omega n squared is equal to omega n squared f of s. So closed loop transfer function here, which is output x of s over input of the system, gonna be omega n squared in s squared plus 2 zeta omega n s plus omega n squared. So this closed loop transfer function. So if I want to plot this in the unity feedback block diagram before going to the underdamped, overdamped systems, plus minus this is going to be f, this is going to be x. So again, you tell me what I'm going to put here. What I'm going to put here, open loop or close loop transfer function? Open, G. So how to calculate? I taught you a million times. For unity feedback is G1 plus G. So if you do that, I'm skipping that because this is really trivial. This is high school thing. So G of S, open loop transfer function, gonna be omega n squared s squared plus 2 zeta omega ns. Do it. Or intentionally I'm writing as this. Gonna be omega n squared s plus 2 zeta omega n. Guys, look at this very carefully to this open loop transfer function. What do you see? System has what by itself? Not pole. Obviously, we have two poles because this is second order equation from high school. We have two poles. Yes. System has I controller by itself, 1 over S. See what I'm saying? I controller. Yeah, 1 over S. Yeah, this is, see, this. So you have to put here omega n squared, and we're gonna do in the simulating. S plus 2 zeta omega n parentheses. Clear, guys? Now you tell me how many poles this system has. Closed loop transfer function. How many poles? What are the poles? The roots of numerator or denominator? Poles. Go and look at your notes. Poles, I told you 10 times. Denominator is the poles. Numerator roots are, what's the name of those? I told you, zeros. That's right. How many zeros this system has? How many zeros this system has? Huh? How much? 2. Okay. Do you see any equation here? So there's no zeros here. Because there's no equation. How many poles this has? How many poles this has? How many poles? Two. Because poles is the roots of the denominator. So, saying that, so the poles of the system, we're gonna solve for that. Okay, these are the poles of the system. So from high school, you know that P1 and 2 poles gonna be minus 2 zeta omega n minus b plus minus b square 4 zeta square omega n square minus 4 AC minus 4 omega n square divided by 2a. A is 1. I hope that you know this from high school. Second order equation. Everybody knows that, that's right? Hopefully. Yeah. So you can simplify this as this 4 comes out, 2, all of them goes. Okay. So remaining gonna be minus zeta omega n plus minus omega n square omega n in, because comes out. You're gonna have zeta square minus 1. So these are poles of the second order systems. Now we have 3 scenarios. A, if your system is underdamped, zeta is smaller than 1. If the zeta is smaller than 1, what's gonna happen for these guys? What's gonna happen for this term? This becomes positive or negative? Positive or negative? Yeah, so we don't have the root square of negative. So you're gonna have I, you have to write like this, 1 minus zeta square. So the poles of the system, if your system is underdamped, becomes minus zeta omega n plus minus I omega n 1 minus zeta square. I'm not done. Hold on. Okay. So you have two poles. Okay. Two poles. And the poles are real number or imaginary number? Real number or imaginary number? Yes. Has a real part and imaginary part. Okay. Imaginary part. So if I plot this, okay, real, imaginary. So the real part of that, see, this is real part. This is in the left hand side, minus zeta omega n, say here. Suppose that here is zeta omega n minus. And plus n this. Suppose that here. One of them is here. Another is, suppose that here is omega n 1 minus zeta square. And here is minus omega n 1 minus zeta square. So the poles gonna be located here. These are the poles of the system. We name this as a pair of complex conjugate poles. Complex conjugate poles. It's technical name for underdamped system. A pair of complex conjugate poles. Obviously, it says that your system is stable because it's in the left hand side. Okay, but we're gonna analyze this. That this leads to what eventually? A pair of complex conjugate poles. When I'm saying that zeta is smaller than 1 for second order system, I'm not meaning only for mass spring damper, also for RLC circuit, also for tank of the water in series. So your RLC circuit can have, for if it's under damp, can has a pair of complex conjugate poles. Tank of the water in series can have a pair of complex conjugate poles. That's why I'm sticking to zeta and omega n. I don't care what are making that zeta omega n and zeta omega n and zeta. Okay? Now, what was the question? No, I didn't. I didn't say that. I didn't say that your system is if you have a pure complex poles, if you have pure complex poles, where is that? Where I wrote it. Ha! Your system is marginal stable, man. A pure complex poles, your system is marginal stable, like a pendulum problem. Do you see any pure complex poles here? Do you see pure complex pole here? It has real part. It has real part. See? Yeah. What? So, do you see this? Do you see this? So, what are the poles of this system? Okay, what you are telling me, so what you are telling me now has both. Again, we're gonna have margin stable system. What you are telling me this? I mean that you are terminating your question. See what I'm saying? Okay. See what I'm saying? So you are telling me that system has a pure imaginary poles is marginally stable, means oscillating forever. Then you are telling me now system has real and imaginary poles, a pair of complex, again is marginally stable. Why? Why is that? So look at here. This is pure, a pair of pure imaginary poles. Do you see that? So your system gonna oscillate forever. Okay? So what about this? They are pure imaginary poles? Why? I want that you give the answer. Yes, because has a real part. Has a real part. See that? Here is zeta omega. You got it? Yes? Good. Yes. We're gonna go there. Don't rush. Okay? I'm gonna torture you by huge mathematics. We are not yet there, okay? See? Okay, guys. Before going ahead, I have to simplify this. What was the name of this? I taught you. What was the name of omega n? Yes. What was the name of the zeta? Yes, damping ratio. So it says your natural frequency being damped. So we name this as omega d. Omega n 1 minus zeta square. The name of this technically is damped natural frequency. Damped natural frequency. Damped natural frequency. So if your system is under damped, I'm not done yet, okay? Can I go to the next page? Yes? So if your system is under damped, the poles of the system simply can be written as a pair of complex conjugate poles plus minus I omega d. So if I plot this here in the complex plane, real, imaginary, gonna be this. Here is omega d. Oh, sorry. Reverse. Here is minus zeta omega n. Here is omega d. Okay? Understand? So these are poles of the system. When the system is under damped. Now if I connect these guys as it is, a pair of complex conjugate poles. If I connect this to the origin, here, the origin. Can I do that? Yes, because I'm a professor. And then, if I want to find this hypotenuse. So from kindergarten, you know that x squared is omega d squared plus zeta omega n square, right? Because here also is omega d. Everybody agree? Omega d is omega n square 1 minus zeta square plus zeta square omega n square. This with this goes, and the result is omega n square. So the hypotenuse of this triangle is omega n, natural frequency. Interesting to know. So here is natural frequency. It doesn't matter that the pair of complex conjugate poles is here or it's here. All of them when you connect to here, this distance, if you come to my root ME430 that I'm gonna teach root locus, we're gonna see that why I'm teaching it down here eventually. Here is omega n, here is omega n, here is omega n, natural frequency for a pair of complex conjugate poles. I'm deleting this because I have to teach more. Okay, and also this angle sometimes needed. Oops. This angle I'm saying as theta angle. You know that from this triangle, tangent of the theta is omega d over zeta omega n. Because this is omega n 1 minus zeta square and is zeta omega n. You can find that angle is tangent inverse of the system damping ratio function. It only depends on the damping ratio. I don't care the system is the RLC, tank of the water, whatever. Okay. See what I'm saying? Okay. Now, let's go to the second case. B. If your system is critically damped. So, look at here. This was our original poles. I'm just writing here before going to the A. So it was poles of the system that we derived originally was minus zeta omega n plus minus omega n zeta square minus 1. See, I'm just copying from here. When zeta is 1, how much is this, guys? Simply, how much is this? When zeta is 1? Huh? How much is this? 0. So you have two repeated real poles minus zeta omega n. Two repeated means P1 is minus zeta omega n, P2 is minus zeta omega n. So if I plot this, real, imaginary. For underdamped system, we had the pair of complex conjugate poles. But for the critically damped system, because here is zeta omega, remember? Here is zeta omega. You have two repeated poles over each other because it's on the real axis. See what I'm saying? Yes? Everybody? You have two repeated poles. Now let me go to the third case. Your system is overdamped. It means that you have excessive damping. So P1 and two poles of the system is zeta omega n plus minus omega n zeta square minus 1. So this is positive or negative if zeta is greater than 1. Positive or negative? Yeah, it's going to be 0. Positive. So you have two real poles. So your P1 gonna be minus zeta omega n plus omega n zeta square minus 1, and the P2 is minus zeta omega n minus omega n zeta minus 1. You have two real poles. Two real poles. If I show here, it says this is zeta omega n. Plus a number, minus the number. So if I show here, your system gonna be like this. For overdamped system. Plus a number, minus a number. So these is for overdamped system. These two real numbers, or for critically damped system, and these two are for underdamped system. For underdamped system, you have a pair of complex conjugate poles. For critically damped system, you have two repeated real poles. For overdamped system, you have also different real poles. Different. But all of them, they are in the left-hand side. Means that your system is stable. But how is it stable? How it's gonna behave? This is I have to teach you. Left-hand side. So it means that your system is stable. Okay. So, can I go ahead? Yes? Okay. Now, case A. If the input to the system is impulse, as we did with the first order system first. So, if you apply the Laplace, f of s is going to be how much? 1. Remember? And I'm going to consider when your system is underdamped system, meaning zeta is smaller than 1. Based on whatever I taught you, you have two complex conjugate poles. Plus, minus zeta omega n plus minus I omega n. And we know that x over f was omega n square s square plus 2 zeta omega n s plus omega n square. So this can be written as, because this is 1. So x is equal to output of the system omega n square. So we know the poles. You can decompose in this format. S minus P1 in S minus P2. That's right? Second order system. We know the poles. Everybody understand? Or rectangle plus, huh? What? Yeah, let me put minus because I don't want to change the signs. That's right. We can write like this. Okay. So, and now we have to do this. A over S minus P1 plus B over S minus P2. Okay? Understandable? Now I have to find A and B. So you know that it's gonna be A S minus P2 plus B S minus P1 S minus P1 S minus P2. This is equal to how much? Omega n square. So if I write this, it's gonna be A S minus P2 plus B S minus P1 is equal to omega n square. If I reorder it, it's gonna be A plus B S plus B P1 minus A P2 gonna be omega n square. We have done this for the first order systems. This is 0 because there is no S in this side. This is equal to how much? Omega n square. From here you get A is equal to minus B. If you put this here, you get B P1 plus B P2 is equal to omega n square. So from here you get B equals to omega n square P1 plus P2, and the A becomes minus omega n square P1 plus P2. Everybody agree? Yes? Also, guys, we have a minus here. I made a mistake because I'm teaching from my memory. So here gonna be this. I have no notes. I hate professors that they are teaching from notes. It means that they have no knowledge. Okay, so minus P1 is gonna be, so it's gonna be P2 minus P1. P2 minus P1. And here is also gonna be P2 minus P1. Let me double check. Minus B P1 minus, okay, that's right. Minus plus B P2, yeah, P2 minus P1 and P2 minus P1. Now that's right. Okay. Now let me calculate A and B. Get here, guys. Your P1 was minus zeta omega n plus I omega d. Your P2 was minus, for underdamped system, minus I omega d. So your B gonna be omega n square P2 minus P1. See here? There we go. So having that equals to omega n square minus zeta omega n minus I omega d minus zeta omega n minus I omega d. This with this goes away. So what you get is omega n square over minus 2I omega d. There we go. And we know that the A equals to minus B. So your A becomes omega n square 2I omega d. Here we go. So what I'm going to do, I'm going to put it here. So your x becomes omega n square 2I omega d. Look at here. Because they are the same. Only the same. S minus P1. S minus P1 minus, because we have a minus here for P. S minus P2. Here we go. Now I want to find its in the time domain. What I have to do, guys, I told you a million times. I want to back to the time domain. What I'm going to, yes, inverse Laplace. Which function gives you such a Laplace? Now you know it. Go look at your Laplace of EAT gonna be what? 1 over S minus A. That's right. Yes? Everybody, you have in your notes. So x of t gonna be omega n square 2I omega d. Here you're gonna have e p1t minus e p2t. Okay? Can I go ahead? Yes? I'm in the next page. Can I? Okay, so for the input of the impulse, x of t gonna be omega n square 2I omega d. So e minus zeta omega n, because your p1 was this, plus I omega d in t minus e minus zeta omega n of p2 minus I omega d in t. Here we go. Obviously, you can factor out that this e minus zeta omega n. So this is equals to omega n square 2I omega d e minus zeta omega nt e plus I omega d minus e minus I omega d. Bear with me. Using the Euler series that I taught you, you can like this inside, like this inside. This part. Cosine omega d t plus I sine omega dt minus, because I told you Euler series expansion, Euler series, right? Or Euler. So cosine omega dt minus I sine omega dt. This cosine with this cosine, you're gonna have 2I. So your x of t finally becomes omega n square 2I omega d e minus zeta omega nt 2I sine omega dt. 2 with 2, I with I. And now look at here, guys. There's no magic. This can be written as this: omega n square omega n 1 minus zeta squared. This one of these goes to the hell. So the final answer for the second order system, which is underdamped, is omega n 1 minus zeta squared e minus zeta omega nt sine omega dt. Bingo. You don't know. You don't need to know the process. You only have to know the final answer. Okay, but we are engineers. We are not mathematicians. We have to visualize this by graph. What was the name of this function I told you? No. If you increase time, this goes to how much? Well, if you look at here, if you increase time, e to the power of minus eta goes to how much? Yeah. What was the name of this function? I told you. Look at your notes. It goes to 0. Decaying term. So what's the name of this function? Obviously, harmonic. That's right. Means oscillation. So if you multiply this by this, because it's going to go 0. So you're going to have a marriage between these two functions. I'm plotting here. See? Right? So you see that you have a transient response that is oscillating for underdamped system and a steady state that goes to 0. Here we go. So we found the solution. For underdamped system, this underdamped system, x over t, can be massive spring damper, can be RLC circuit, can be tank of the water in series, can be satellite, can be whatever. Second order system for now. Then I'm going to extend it to higher order systems. Okay? Whatever it is, if your system is underdamped or the poles of the system they are dominant, I'm going to explain the ones they are underdamped. And if you apply impulse as the input, this is the input of the system. Here we go. This is input. So system going to be like this. Let me change the color to visualize this. You have a transient response that is oscillating. Why oscillating? All of you look at here, guys. All of you. This is important. You have a pair of complex conjugate poles. Means that you have I omega d here minus I omega d here. Real part here. Okay? Because of this part of the pole is oscillating. Why? I want to visualize the mathematics. Look at here, guys. This ended up to what? Ended up to sine, oscillating part. Real part ended up to decaying part. This is the real part. See? So, because you have pair of complex conjugate poles, you have a transient oscillating, then converging to 0 because of this real part. See what I'm saying? Yes? But remember, for the first order system, we had this response. Remember, for impulse, we had no oscillation. Exactly. Never ever. Okay, because first order system cannot have a pair of complex conjugate poles. Cannot. See what I'm saying? Physically cannot, first order systems. And that's why first order system never oscillate. Understand? Yes? I'm not talking about the accuracy. I'm talking about the dynamics of this, how it behaves. This is how it behaves. Like your car suspension system. I'm going to teach you in this course. Okay? Has spring and damper. Yes or no? Your car suspension system. After passing a bump, you feel like this response. Oh my God. You feel this response after passing a bump? Yes or no? On your body? Yes? Huh? So this, so I'm not expecting how much. I'm saying you experience this. Yes or no? Okay? Yeah. So that because your system has a second order system. Understand what I'm talking about? Because your system, your car suspension system has a pair of complex conjugate poles. See what I'm saying? Yes? Huh? Understand? Everybody? Your car suspension system has a pair of complex conjugate poles. Very good. This is a real visualization of mathematics. So I'm going to stop it here because we have to talk about this. This was for the impulse for underdamped system. So we're going to apply for the critically damped system. We're going to apply for the overdamped system. And I'm going to show you for critically overdamped system, this oscillation goes away. It's going to behave like as first order systems. Okay? Okay guys, have fun. I'm done. Too much teaching today. Thank you. Thank you.